Thank you, and thank you for the organizers for inviting me. So I'm talking about, the title is Random Orderings and Unique Ergodicity of Automorphism Groups. So the topic concerns many different structures, actually, many of those listed in Lotzi's first slide and some others. I'm going to talk just about one or two specific examples and how these two things are related to each other. So I'm going to start with one specific thing. Then I'll say a bit about how that relates to automorphism groups, go back to the details of the specific case, and then give details of the application. So let's consider finite graphs. Those will be our structures of interest. So here's one. And vaguely, the first question will be, are there special vertices, or can you distinguish among the vertices in some natural way? Well, in that generality, of course, you can. For example, you can look at the degree of a vertex. But what I want to be natural is actually quite restrictive. So, of course, it should be invariant under isomorphism of graph. But the special condition, it should also be invariant under taking induced subgraphs. So just to remind everyone what an induced subgraph is, if you take, say, those three vertices of this 6-vertex graph, the induced graph is this graph. It's the graph consisting of those vertices and all edges that join those vertices that are in the original graph. So it's a special kind of subgraph. All right, now I still need to say what I mean by distinguishing among the vertices. So the way I want to do it is by, first of all, I will allow randomness. But what I want to do at random is pick a linear, in other words, total, ordering of the vertices of G at random. So random linear ordering of the vertices. Okay, so probability measure on such things. So given a graph G, I associate to it some probability measure mu G on all V factorial linear orderings. Okay? So the assignment of G to mu sub G should be invariant under, or equivariant with respect to isomorphisms, and respect induced subgraphs in the following way. So if I have a big graph G and an induced subgraph H, and any particular linear ordering on G induces a linear ordering on H. And so if I take a random linear ordering on G, that induces a random linear ordering on H. And so under this restriction map, the measure on orderings on G should induce the measure on orderings of H. Okay? Those are the two conditions. So this and isomorphism invariance. Those are the two conditions I want to impose on graphs. Now, of course, if I take the uniform ordering on all vertices, that trivially satisfies both conditions. And that doesn't, of course, distinguish among the vertices at all. So the question is there a way of doing this that does distinguish? In other words, one that isn't the uniform distribution. Okay? Now, I don't think this is such an easy question. So let me start with an easier special case, in a sense. Suppose I consider, instead of all graphs, only, so these are finite graphs, only finite paths. All right? And then only induced subgraphs, which are paths. All right? Then it's easy, right? To get a non-uniform one, I can order it left to right or right to left with equal probability, and that's preserved under isomorphism and an induced subgraph. Oh, and I forgot to mention, all this work is joint with Omer Angel and Alexander Kekris. We haven't quite finished writing the paper yet. Okay, so that was easy. What about graphs that are unions of paths? Disjoint unions of paths. That is, all of whose connected components are paths. Okay? Well, one thing to notice about the original condition that I asked is that if I have a complete graph or an empty graph, no edges, then necessarily, because all permutations are automorphisms, the ordering in that case must be uniform. So in particular, if I pick a subset of vertices, which is an independent set, then the order on that set must be uniform. Okay? And independent sets are unions of paths. Okay, so that's the question. So let me let you think about this for a minute. Does anyone have a suggestion about how to get a non-uniform, consistent ordering? So those will be called consistent when they satisfy those two conditions.
Order by component size first, order by path length first, given that they're distinct, at least not close.
Okay, so let's look at that suggestion. So maybe the first step is to order by component length. Well, the problem with that is if you take induced subgraph, that can completely change the component length. But it's good you mentioned that because I just want to show you what the difficulties are of trying to solve this. Any other ideas? Yes?
Try to do a uniform permutation among the components and within each component, uniform permutation of the vertices.
Oh, you mean so we'll order them all together by blocks in a uniform way, and within each one. Okay, so does that work? Do you have an answer to his question or a different suggestion?
Linear order such that each of those paths should go in one direction, either this or that.
But you also have to order all the vertices together.
Right.
So I have to order, say, how does one path relate to another path?
Every linear we take with the same probability, every linear order which so that each path appears in the right order in that linear order. Of course, there are two ways.
You mean left to right or right to left?
Yes.
Yeah. Okay, so, but the problem with that is, let me make this a little bit longer. You can take an induced subgraph, which, for example, has two components, right, and then those two together will be oriented in the same way by the induced property, but that's not the ordering you originally gave it. Okay, so let's go back to Christian's suggestion. So you said order them by blocks and then each one uniformly. So does that work?
No, because if you look at the endpoints, that will put the two endpoints of a path next to each other. So
Different paths.
of the same path. So you look at, say, the 4 points, which are the 4 endpoints of the two long paths. Those two and the other two.
Yeah.
Then you won't see the uniform order on those 4 points.
Right, exactly. Though that's an independent set. but you don't see the uniform ordering on it because these two are both less than those two, or they're both bigger than those two. Okay, so I don't want to spend too much time on this example, but I just wanted you to see what the difficulties are. It can be done. I'm not going to show you how to do it, but let me tell you. Two more questions. Similar to these two, first, again, consider the case of connected graphs, say trees, more general than paths. So paths was easy. What about trees? It can be done. I won't tell you how to do it. But what about forests? I don't know the answer. Okay, now actually among the examples, and let me give you two other types of examples.
So what is the question? Does there exist a forest for which there is no?
Does there exist an assignment of orderings to all finite forests? Right, to each finite forest there's an ordering, a random ordering, which satisfies that it's invariant under isomorphism and induces the correct ordering under restriction. Okay, so the original question, but just restricted to a certain subclass of graphs. Of course, there's plenty of subclasses of graphs that might also be interesting. I just mentioned these ones to start out. One could also consider hypergraphs, metric spaces, and a bunch of other types of structures. Now, of the ones I've written down, so there's a theory that gives some applications. And it applies to all graphs, to all hypergraphs, to all metric spaces. But these other examples that I wrote down, it does not apply to. So in the sense of applications, for these other ones, it doesn't matter whether the answer is yes or no. Although I think in and of themselves, they're interesting questions. So I'm going to concentrate on graphs. If there's any time, I might say a little bit about some of the other structures. So what is the answer for graphs? The answer is no. There's only the uniform ordering that gives a consistent random linear ordering. Okay? Now, so before I tell you how we prove that, let me tell you briefly what the application is, and then I'll come back later to the details of the application. So, there's something called the random graph, not a random graph, the random graph. So it has an infinite countable vertex set, say the integers, doesn't matter, and some edge set, which is not random. But it's called the random graph because if you, for example, put an edge between two vertices with probability half independently for different pairs, then almost surely, up to isomorphism, you'll always get the same graph. And that's called R, the random graph. You can characterize this random graph pretty easily, R, in the following way. It contains, as an induced subgraph, every finite graph. And it's ultra-homogeneous, which means if I have an isomorphism between parts, induced parts of the graph, then it extends to an automorphism of the whole graph. So there's a unique, it's pretty simple to prove, there's a unique such graph up to isomorphism, and that's the random graph. So in the sense of graph limits, it's the limit of the Ernst-Rényi graphs in a certain sense. Certain boring sense. Okay, now, so this is a graph. I talked briefly about the automorphisms of this graph. So that's a group. It's a closed subgroup of S infinity, which came up this morning. The set of permutations of all integers with the natural weak topology. And the fact that there's only the uniform ordering for consistent orderings implies that this group, automorphisms of R, is uniquely ergodic. I'll say what that means later. Okay, so that's what I'm going to do. So let me go back now and say why it is that there's only only the uniform ordering for consistent. Any questions up to now? Yes? Yeah, so a group, I'll define this later, but since you asked, a group is uniquely ergodic if every minimal action is uniquely ergodic. Whenever it acts topologically, so that every orbit is dense, there's a unique invariant property measure.
The space it's acting on is?
Anything. No matter how it acts minimally, if it acts minimally, then there's a unique invariant measure. I'll define all this later and give some examples. Any other questions on what I've talked about as opposed to what I haven't talked about yet? Okay. So we actually prove a quantitative version of the uniqueness statement that there's only the uniform measure for a consistent one. So how do we quantify it? Well, suppose we have this assignment of measures on orderings only up to graphs of size n. Then, if you have a graph H of size k at most n, then we can say how close mu sub h must be to the uniform ordering in terms of n. So I'll denote, so remember, an ordering of a graph is just an ordering of the vertex set, but I'll just denote less than sub h for an ordering of the vertices of h. Okay, so mu sub h gives a number to this particular ordering, less than sub h. And to be uniform, it would be equal to 1 over k factorial. So how much does it differ? So for all orderings, it differs by most some constant depending on k times the square root of log n over n. The fact that square log n over n tends to 0 as n tends to infinity is what tells us that we only have the uniform if we do it for all graphs. Okay, so how do we prove that? We don't have any proof, basically, which is not quantitative in some way, which can't be made quantitative. Well, we're going to prove something which is somewhat stronger and will look quite different. So given this ordered graph, H, we find, it's of size k, this graph G, which will actually be of size n, such that no matter how you order G, if we look at the embeddings of H into G, so because of isomorphism and embeddings of H into G as induced subgraphs. So by embedding, I'll always mean as an induced subgraph, an isomorphism to an induced subgraph. So by the two properties together, we can conclude something about embeddings. So we consider all embeddings of H into G. And some of them will preserve the ordering. In other words, the ordering on G will induce the corresponding image of the ordering on H. Some of them won't, but look how many, the proportion that do preserve the orders.
An embedding of H into G, you mean it preserves edges and non-edges?
Yes.
Finding H as an induced subgraph in G?
Yes, exactly. Okay, so it differs from 1 over k factorial by that same right-hand side that we want to get in the theorem. So an ordering either preserves, an embedding either preserves the order or it doesn't. If I were to choose an ordering at random from either G or H, for a given embedding, the probability would be 1 over k factorial that it does preserve the ordering. But I'm not doing anything at random here, except if you want, you can consider uniform embedding. Okay, so it's a different type of a statement. The orderings in this other thing here are not random, right? But you could still think about comparing to randomness. So what I want to do is first show you how this statement in the middle board implies the theorem, and then say how we prove this statement. Okay?
So just as an example, if H was the empty graph, then G would be the empty graph.
No.
On the same size, or no?
No. H is of size k, and G is of size n.
Empty, you mean no edges?
I mean, you could. It would work if you took the empty graph, but you don't have to. Because this, right? Okay. Was there another question? Okay. All right, so let me say why this middle statement implies a theorem. Okay, we want to prove something about random orderings with respect to mu sub G and mu sub H. So well, we're going to say something about a fixed ordering less than sub H. So let's keep that one fixed. Let's pick a random ordering less than sub G according to mu sub G. And now our middle statement says something about all embeddings. So let's choose an embedding uniformly at random. I'll call that phi from H into G. So given, if we're given that ordering on G, and given the embedding, we can see whether it preserves the orders or not. And let's call A the event that it does preserve the orders. That's something about which we're making an assumption. Excuse me? Yes, the less than sub H is fixed. So it's fixed in the statement here, and we need to prove something about all orderings on H, so we'll just fix one. Okay? So this event A depends on that ordering on H. But I'm just going to not write out that dependence. Okay. So what are we assuming? What's the probability of A given the ordering on G? Well, that's just the proportion of the orders, of the embeddings that preserve the two orders. So we're assuming that this differs from 1 over k factorial by some bound B, that right-hand side. Now, what about the probability of A given the embedding? Well, mu sub H and mu sub G satisfy a hypothesis of consistency, right? That says no matter how you embed, you get the right distribution. So you fix phi, then the probability of A is mu sub H of that particular ordering. Okay? So those are our two assumptions here. So what do? Well, we just uncondition. So in the first one, if you average over orderings on G, that tells you the probability of A differs from 1 over k factorial by no more than B. And the second one tells you that the probability of A is equal to mu sub H of this order. So if you substitute the second one into the first one, you get the theorem. Okay? So now I want to say how we find this graph G. So we're given an ordered graph H. So some of you may know how to do this already. Anyone have a suggestion? What? Right? Can you be a little more specific? No, actually, it's an Erdős-Rényi graph. Now, not a typical one, because there are a lot of conditions that have to be satisfied, but you just prove that you can find one of them that does it. So take G according to the Erdős-Rényi measure on n vertices with probably 1/2 of joining an edge between any pair at random independently. And I want to show that with positive probability, it has the properties I want. Now, so these properties here in the middle. Okay, so there's two things to consider. Embeddings into G, or in other words, really think about an injection of the vertices of H into the vertices of G and whether that turns out to be embedding or not. And second, the ordering. Does it preserve the ordering? Which doesn't depend on the edges. Okay. Well, there's a lot of randomness here. There are about n squared independent choices being made. So anything that I ask for, almost anything I ask for, is very highly concentrated. It's very likely to be very close to its mean. And I'm going to be asking for how many things to happen? N factorial things, right? For each ordering of G, I asked for something to happen. So the n factorial things. Now, n factorial sounds big, but actually it's not, right? It's only about e to the n log n. and my concentration is of order e to the minus n squared. So that actually gives me room, and it turns out it gives me just enough room to get that particular bound. Now, I'm not going to write down all the details. It's not very hard. But the point is, where does the 1 over k factorial come from? Well, each particular embedding of h into g either preserves the order or it doesn't. If I look at only so here's the image of h. If I look at only those k vertices in here, that's all I need to look at to determine whether it's an embedding and whether it preserves the ordering. And there are, given the orders on G and H, there are 1 over k factorial of the injections that preserve the embedding compared to all. There's only one. So that's where the 1 over k factorial comes from. And because everything is very highly concentrated, it works out. Okay? Should be plausible. And if you went home, you could write down the details, I hope. Okay, people are nodding. Sounds good. All right. Now, before going on to the second part, we don't know how sharp that upper bound is. If you see the structure of the proof, we didn't use anything about the ordering on G. So we just don't know what the ordering on G is. We use this thing, you say, well, whatever the ordering on G is, it's as good as we want it to be on average. Of course, it could be much better because the ordering on G has to satisfy all sorts of properties. We didn't use them. So I suspect that's not sharp, but, and so we have a lower bound. I won't write it out, but a lower bound does not have that square root, so it's smaller. I'll just say that. So you can find a non-uniform ordering that's non-uniform by that much, by that amount. Okay. So now let me go on to the application. Any questions on this concrete part? The rest is going to be somewhat abstract. Okay, so I want to talk about an application to ergodic theory. So let me set the general stage. Suppose gamma is a topological group. X is a compact space. And gamma acts on X continuously. So that means every element of the group is a continuous bijection of X. And it's a group action. And in fact, gamma is not discrete. So in fact, the action as a map on gamma cross X is continuous. That's what a continuous action means. Okay. Now, the question, so one of the fundamental questions in ergodic theory is, what can we say, so it's a very vague question, about gamma invariant Borel probability measures? So gamma invariant, so if mu is a probability measure on X, and you act by gamma, then that pushes forward mu to gamma star mu, and that should equal mu for all gamma. That's what it means to be gamma invariant. So what can we say? So from now on, measure will mean a Borel probability measure. So that's a general question. For example, does it exist? Is it unique? Well, there's a nice condition on gamma which will always provide existence, and that's called amenability. So gamma is amenable if for all such x there exists an invariant gamma invariant measure on x. So z to the n are examples of discrete groups that are amenable. A free group on 2 letters or more is non-amenable. I'm not going to say too much about that because the focus here is really on uniqueness. Well, there are some cases where it obviously is not unique. It could not be unique. It makes no sense to ask it to be unique. If, for example, x decomposes into 2 invariant parts, and if it's amenable, say, so then there's an invariant measure on each, and any convex combination of them will be invariant. So you can't expect to have uniqueness without some severe restriction on x. And that condition is called minimality. So to be minimal, this means minimal for gamma, means that every orbit is dense. So an orbit is the image of a particular fixed point gamma under the group, fixed point x under the group, all the images. Okay? So every orbit is dense. So that's called minimal. Okay? And you can't decompose it. Okay, then it might be unique. So let's look at some examples. Well, suppose gamma is compact. So I didn't say what x is, but x is anything that it acts on. It's minimal. So then it is unique. So why? So gamma has, in this case, a Haar measure, which is unique, a probability measure which is on gamma, which is invariant under the gamma action on gamma. And if I have any invariant measure on x on which gamma is acting, I can average that measure by acting on it by elements of gamma and averaging over gamma. And that will, by invariance, give me the same measure. But by uniqueness of Haar measure, will give me, any 2 measures will give me the same. In fact, if I take a particular point and take the limit, that will give me the same measure. So basically, the uniqueness here is arising from the uniqueness of Haar measure which is the uniqueness of the gamma action on itself. So that's going to come up in a moment. Excuse me?
Where are you using minimality in this reason?
Right. So yes, I should have taken an orbit. I should have taken an orbit and taken the the measure on gamma pushes forward to a measure on the orbit, which is, because gamma is compact, the orbit is actually all of x. Right. So the I'm sure there's a better way of saying this, but if you consider any measure on x as an integral of Dirac measures, integral by that measure, and then you apply gamma to it, it's just going to be, it's not going to change by invariance, but then you're going to be integrating always the same measure, this image of the Haar measure. Okay, so let's look at, this is a kind of trivial case. So suppose gamma is the integers. Okay, now let me say how it acts. By irrational rotation on a circle. So this came up earlier. So you pick an irrational number and add a number alpha and add alpha to x mod 1. So this is minimal by a Kroneker's theorem from the 19th century. Now in this case is, so Lebesgue measure of course is invariant. Is it the only invariant measure? Yes. This also goes way back, although I can't say to whom. And there are various ways to prove that it is the unique invariant measure. Now, there are other actions of the integers, minimal actions, however, where there's more than one invariant measure. But that's not so easy to construct. There's none so easy that I know of that I could present it to you. So I won't. No, remember, it's got to be ergodic. I mean, minimal. That's the tricky part. It's not that hard, but it's annoying, and you got to write out a lot of stuff. But yes, that's the way one would do it. Find a particular. Okay. Now, this example of the integers is in fact typical in the following sense. That, in fact, there's non-uniqueness for every Polish, non-compact, locally compact, amenable group. Probably. At least if it's discrete, that's definitely true. It's probably true in general. Group.
Oh, it's an almost theorem. This is not sure of a hypothesis.
Well, that's true too. Right. Okay. So this then raises the question, besides compact groups, are there groups, topological groups, for which every minimal action has a unique invariant measure? So when gamma, x being acted on by gamma is called a gamma flow. So the question is, when is every minimal gamma flow uniquely ergodic? So uniquely ergodic means there's a unique invariant measure. Well, that sounds hard to answer because you have to consider every possible minimal action. However, like the example of a compact group, it turns out that there's only one that you need to consider. It's called the universal minimal gamma flow. So what is that? So this is something whose existence you can prove abstractly. So this is a flow, gamma flow, such that just as we saw over here, every other minimal action factors through it. So in this case, not everything was visible because gamma was acting on itself. But there's really, in general, this other space that gamma is acting on, m of gamma. So to say that x factors through m of gamma means there's a gamma map f from m of gamma to x. A gamma map is one that intertwines the gamma actions, commutes with the action of gamma. Okay? So you can figure out what happens on x by knowing what happens on m of gamma and just pushing it forward by f. Okay? And it's not so hard to show that if there's a unique invariant measure for m of gamma, then there's a unique one for x. So it reduces to figuring out what happens for the universal minimal gamma flow. So let me just write, so for gamma compact, m of gamma equals gamma. So when this property holds, when every minimal gamma flow is uniquely ergodic, we will say that gamma is uniquely ergodic. So the question is the action on m of gamma uniquely ergodic? Okay? Now, m of gamma, so when gamma is compact, it's perfectly nice space. But if gamma is infinite and discrete, for example, it's a very nasty space, not metrizable. So the interesting thing, though, is that there are many situations where you can still calculate m of gamma. With non-discrete, the non-locally compact. And the first, in this context, was due to Glasner and Weiss in 2002. Excuse me? No, Benji Weiss. Yeah, Glasner and Ellie Glasner. Ellie Glasner, Benji Weiss. If I put the B in, that wouldn't help. Okay. So they showed that the universal minimal flow for S infinity, all permutations of a countable set, say the natural numbers, is equal to, now you'll see what all this has to do with the first part of the talk, all linear orders of this countable set, say the natural numbers. For example, it could have the order type of the rationals, right? So it's still big space. Well, what can you deduce from this fact that that is the universal minimal flow? Well, it's not so hard to see that therefore S infinity is uniquely ergodic. So I'm considering all permutations of the natural numbers and all linear orderings. And I want to say the only measure is the invariant measure is the so-called uniform measure. What do I mean by the uniform measure? If I have any finite set of points, the ordering on that finite set is uniform. And there's a unique such measure. And because this is the universal minimal flow, the group is uniquely ergodic. Okay? That should be plausible, at least. Not many people are nodding. Yes, well, I have a vigorous nod over here. It makes up for those who aren't. So, if anyone has any questions, does anyone have any questions on that?
I mean, when you say this minimal, what are you assuming about the structure of this M of S infinity? Is it
So this
algebra or is it?
yeah, so it's a compact space. All these minimal flows are always compact spaces. So okay, an ordering is a relation, right? It's a subset of the product space, and so that the product space has a Tikhonov topology. So this is on n cross n. Well, this is just discrete. Sorry. So it's a 2 to the n cross n, which is Tikhonov. Okay. So this is a closed subset of compact space, compact. Okay, so this was the first example of a uniquely ergodic group other than compact groups. And there's actually one other class which I didn't mention, which are whose behavior is even more extreme, and they're called extremely amenable. An extremely amenable group is one such that every action on a compact space has a fixed point. So there's an invariant measure, which is a delta measure. Now, those aren't so easy to come by. In fact, I think the first example of that was by Gromov and Millman, and used concentration phenomena. 1983. And this was the unitary group of Hilbert space, separable Hilbert space. So unlike the unitary group of finite dimensions, the unitary group in infinite dimensions is actually extremely amenable. Okay, so extremely amenable groups are definitely uniquely ergodic. Every minimal action is just an action on one point. So other than those trivial examples of compact and extremely amenable, this was the first example of uniquely ergodic. Okay, so what we do is give the next examples. And in particular, the automorphisms of R. The random graph. So, for this, I need to tell you very briefly about an important paper of Kekris, Pestov, and Todorcevich in 2005. And what they did is give many more examples of calculations of universal minimal flows for closed subgroups of S infinity. Now, it turns out that to do that, there are all sorts of connections to other areas of math. Which are important. Model theory is one, and Ramsey theory is another, which is crucial to this. I think Yarrick is going to talk about maybe something related to this. Okay. So, as an example, for R, the random graph, so now the automorphisms of R are just some of the permutations of the vertex set. So this is a closed subgroup of S infinity. And M of that, that's its universal minimum flow, turns out to be the same as the universal minimum flow for S of gamma, of S infinity. Different group acting, but the same space. All linear orderings of the vertex set. Now, they knew that back in 2005, but that does not imply immediately that there's a unique invariant measure. Right here, it was easy because you can do all permutations. There's no restriction. Here, there's some fixed underlying graph, and you must respect that. Right? So you can't just obviously make all orderings equally likely. And in fact, if you look at what it comes down to the question that I started with. Is there a unique, consistent ordering, the uniform ordering, on all finite graphs? So I think I'm out of time, so thanks.
Or because of the extension property of the rubber graph.
Well, if I have in R, I may have 3 points, say, and there's no edge here, but there are these 2 edges, right? And I want to say that the ordering of those 3 points is equally likely to be any of the 3 factorial possible ones. Well, there's no automorphism R that takes these 3 points to all the possible 6 permutations. Yeah. So it doesn't follow just from trivial. You need some other way of doing it. But if you think about it a bit, you can see it's not so hard because you can move it around to different places. So there's a whole theory. There's lots and lots of definitions that go into what kinds of subgroups of S infinity this applies to. Very interesting theory, but anyway, so thank you.